come lubricated, or do you never use it?
No, I've got my own.
Okay.
I remember being in middle school and not getting my first Rubik's Cube and looking online how to properly use it, and the first thing you had to do in every article was to take it apart, put Vaseline in it, and put it back together. I was 10. I don't know how to do this.
It actually ended up destroying those cubes.
I made it, yeah. I didn't use mine for very long, obviously.
My dad's already on board.
Oh, really? It kind of sticks with you once you get really good at it. Because I thought I'm not
Okay, let's start. Sorry. So we're gonna just review polarity molecules very quickly. We'll talk about resonance structures a little bit more detail because we kind of broached the topic last time. And then we'll get into valence bond theory, specifically hybridization. And we're gonna understand how orbitals make these bonds and these shapes, these structures that we've been looking at. So, I'm going to assume that this is okay for most people, because we did in the lab. I think nobody had any major questions. So to find if a molecule is polar, you have to look at both the bonds, how many polar bonds are in there, and what the shape of the molecule is. So if there's an uneven distribution of electrons, it's polar. If it's symmetrical, it's nonpolar. And I gave you the shortcut way to find it. So if the electron geometry and the molecular geometry are the same, and all of the outer atoms have the same electronegativity, it's nonpolar. If one of those two is not true, then it's polar. So, yeah, so we talked about this. We looked at CO2. This was in the lab today even. Not polar. Here's water. That's polar. I'm going to go through this really fast because we've seen this. Here's ammonia. Nice polar molecule. Definitely negative on this side, positive on this side. And then even when you get to these, it's a more symmetrical shape. It's tetrahedral, but not all the what in the world?
Well,
It's a ghost.
Somebody, hold on. I don't know what happened. All right, maybe this is it. Hold on. View, review. I didn't record anything. Maybe somebody is, oh, you know what? Somebody's probably sharing in from home. Anyway, I didn't think they'd have permission to do that, but it's okay. So he was good. No, I think it's recorded somehow. I don't know why. It shouldn't be. All right. So, all right, we've covered this. And it's all, starting with electronegativities. You have to understand the bond, whether a bond is polar or not. We went over this a little bit quickly, but I want to remind you that there are plenty of atoms on the periodic table that break the octet rule. So BF3 is one of them. Boron can have 6 electrons around it, and it's happy. And for that reason, it makes this trigonal planar shape with fluorine. But again, this is one of the trigonal planar. That's the electron geometry and the molecular geometry are the same. All fluorines on the outside, they're all the same electronegativity. So this is nonpolar. And you can see it here. There's no one side of the molecule that is more negative than the other. And then there you go. Tetrahedral, polar, nonpolar and polar. They're both tetrahedral, but one of them has all fluorines. One has 3 fluorines and a hydrogen, so not all the same. Okay, we did all this too, I think. So I'm going to skip past this. And we'll come back and maybe do some examples later, but this is just practice on, again, from scratch, drawing this out, doing the Lewis structure, then getting the shape, and then finally determining if it's polar or nonpolar from the shape. we'll do it again at the end if we have time, okay? So, pretty sure I quizzed you guys on this, but just in case, what is this, polar or nonpolar? 6 minutes left. We're at step 1 of the process. We've got the Lewis structure, sort of. It's not a great Lewis structure, but it works. All right, and then we need the shape, and then from the shape, we would find out that it is polar. So this is a tricky one. Not a trick, but it's a tricky one. There's 4 groups of electrons, 1, 2, 3, 4, around that central atom. It's tetrahedral, and you have to remember that that's not what tetrahedral looks like. Tetrahedral looks like this. It's that 3-dimensional shape, and so we have 2 hydrogens, 2 fluorines. Probably the best way to show the difference is put them like this. It doesn't matter where you put them; they're all in equal positions. And here you can see, hey, these are the more electronegative atoms. These are less, the least electronegative. So really, the dipole moment goes this way for this molecule. It kind of goes in that direction, towards the fluorines. The more electronegative side, or the partial negative charge, is going to be on the fluorine side of the molecule. This is definitely polar. And again, if you use the technique I mentioned, what's the electron geometry, what's the molecular geometry? Well, it's tetrahedral, but all of the atoms on the outside are not the same. So it's got to be polar. Yes?
I forgot, how do you know which ones should be attached to just a single bond and ones that should be like 3D? How do you know which atom?
It should be in the center.
Should be like 3D, like the S
Oh,
3D.
it doesn't matter.
Oh.
So these are all the same positions. So if you imagine this as a 3-dimensional molecule, you can rotate it in space
Oh, yeah.
and put this here and that. So I chose to put the fluorines here to make it easier to see they're on one side. But yeah, they're all equivalent. They're all the same positions basically. Okay. All right, so we'll come back to this idea after this. So, now, if you have more than one Lewis structure, and we've done this already, how do you know which one is correct? Well, we call the multiple resonance structures that you can draw, call the multiple Lewis structures you can draw, resonance structures, and we pick out the best of the Lewis structure using formal charges. So what if we see this molecule? This is benzene, C6H6, and the only way this C6H6 works is if you draw it in a ring and then you have alternating double and single bonds. But why draw it like that? Why not put the double bond instead between these 2 carbons? What about these 2? Well, that's what's over here, and it's alternating, in every other carbon as well. Which one is more correct? Well, and you might say, oh, they're the same if I rotate them. But even if I do an experiment where I make a benzene and all of the carbons are carbon 12, the isotope carbon 12, and one of them is carbon 13, so I know which one's which. Or maybe I put 2 carbon 13s. If I can make a distinction between a double bond between 2 carbon 13s and a double bond between a carbon 13 and a carbon 12. That would be a different molecule. So that's the same thing I'm saying here. These 2 carbons are the same as these 2 carbons. It's just in this one we've got a double bond here, and this one we've got a single bond here. But anyway, which one is the correct one? With formal charges, there's no difference. Everything, if you calculate a formal charge in every atom in these 2 structures, its formal charge is 0. So those rules don't help us. We're looking for the structure with the fewest formal charges, smallest formal charges, and any negatives need to be on an electronegative atom, but that doesn't help us here. So what we have to think now is, well, maybe both of them are correct. And the true answer is that neither one of them is correct. The true answer is it's a combination of these two pictures. Is the correct way to think about what the structure of this molecule is. And if you measure what are the bond lengths of the carbon-carbon bonds, we know that single bonds are longer, than double bonds. And so if one of these was correct, we would see short, long, short, long, short, long, and so forth. But we don't see that pattern. Instead, every single bond is the same length, and that bond length is somewhere between a single bond and a double bond. So really the true picture of benzene is some combination of these two, like an average of these two. And there are a couple ways to show that. It's called the resonance hybrid. So a resonance hybrid is kind of an average or a mixture of the different resonance structures. And I won't say that this is the best way to do it. Probably a better way to show it is like this. So I'm going to put the single bond between all of them, and I'm going to draw the hydrogens. And instead of doing single and double, well, we just found out that the bond length is somewhere between a single and a double. So maybe the bond order is like a 1.5. And so I would put like a 1.5 bond between every single carbon-carbon bond. That is the true picture of what benzene is. Now, that's not a Lewis structure, because Lewis structures show properly where all the electrons are. And that dotted line doesn't mean anything. It doesn't mean 2 electrons, it doesn't mean 1, it doesn't mean anything. So resonance hybrids are, they're not proper Lewis structures, they're just kind of visualizations of what a combination of these two resonance structures are, okay? Now, this circle is actually a very common way to see benzene. In fact, when you draw benzene, while yes, you do see benzene drawn this way a lot, you also see benzene drawn with a circle in the middle instead. These are the same. And the reason for that is because these electrons that make up the second bond in each double bond, so there's 2 here, there's 2 here, there's 2 here, 6 electrons are actually moving around the ring anywhere. They're not just stuck between these two carbons and these 2 carbons and these 2 carbons. They're not localized there. We call them delocalized electrons because they're able to move around the ring. And that's what this circle represents. It represents a giant bond among all of the carbons where those 6 electrons are able to move wherever they want.
If you were to look at a space filling model, would there be a hole in the center?
Not. I'm trying to think. Kind of. Yeah, kind of, but not really. And I'm going to show you why. So we're going to see. So remember, the shape of an atom is determined by where the electrons are, right? And so, what about the electrons in the molecule? Are there electrons in the middle of this ring, or are they on top? And you're going to see there's a little bit of a hole, but not much, and you'll see why when we get to the valence bond theory. All right, so how do we calculate that bond order? So when you have resonance structures, and I want to say, well, what is the actual bond order of the hybrid? Basically, we're just calculating an average. And so for benzene, the bond order is 1.5. And the way I know that is I look at every bond involved in the resonance. So where are the electrons moving? They're moving between these 2 carbons, these 2 carbons, these 2, these 2, and these 2, so forth. And I just basically do an average. So there are 3 double bonds, and there are 3 single bonds. So honestly, a better way to think of this, I don't like that. This math it's not intuitive. But if I look at this benzene structure, there's a single bond here, there's a double bond here, there's a single bond here, and I just keep going around the ring until I count up all of the bonds, all the carbon-carbon bonds, and I'm going to divide that by the number of carbon-carbon bonds. There's 6 of them. So that's the bond order between one pair of carbons, that's the bond order between the next pair, and so forth. So if you do this math, you get 1.5. So that's the average bond order. And this is why we, like I said, we have this concept of bond order. We don't just say single bond, double bond. We have to include bond order because there are fractional bond orders. So the actual bond, bond order between all the carbons is 1.5. Now what's the advantage of that? Well, a single bond is weaker than a double bond, right? It takes less energy to break a single bond. Well, if if this picture was the true picture of benzene, and I'm leaving off all the hydrogens, if this was the real picture of benzene, then I could break benzene very easily along the carbon-carbon single bond area, because it doesn't take much energy to break that bond. It's a lot harder to break a double bond. It turns out benzene is a very, very stable molecule, and one of the reasons it is stable is because it's not single, double, it's 1.5 everywhere. So the bond is actually stronger than what we think it is. So it's actually hard to break that carbon-carbon bond. Benzene by itself is very toxic, but this shape appears in like everything, like in biological things. It's everywhere. It's in cholesterol, it's in hormones. So just this by itself is bad, but it contained in other molecules, it's fine, and very beneficial in some cases. All right. So we know about resonance. This, again, I'm going to remind you that we don't move atoms around. We're only moving electrons around. So if you can draw the Lewis structure a different way with different connections, that's not a resonance structure. Okay? A resonance structure is only where you change where the electrons are. That's it. And so those electrons in the double bond are delocalized because they're not specific to a single bond between two atoms. They are allowed to move around. All right, so remember every bond is 2 electrons. The second part of the double bond is not localized to just 2 carbons. It's actually moving around the ring. Delocalized. And this idea, I mean, we should be comfortable with it by now. This is the basis of quantum mechanics. We don't have to know exactly where an electron is at this point. We can be comfortable with knowing its energy more and realizing it's somewhere in there. The energy is more important in this case. Okay. Again, that combination of resonance structures, that's called the resonant hybrid. It's not a proper Lewis structure. It's just kind of a visualization of what it really looks like. In fact, that's a failing of Lewis structures. So Lewis structure is a very useful tool, but it's not perfect. It can't be used to describe this kind of picture very well. So what if we did nitrate ion? What's the bond order? So now that we know this kind of concept, what is the actual bond order in a nitrogen-oxygen bond for nitrate? So, what do we got to do? We got to draw the Lewis structure, and then we got to see if there's resonance structures, and then we got to calculate the actual bond order using an average. Feel free to try it on your own. I'm going to do it on the board too. But nitrate is NO3 minus. That's not listed there. It's NO3 minus. So 5 electrons plus 6 for the oxygen. There's 3 of them. And then 1 extra electron from the negative charge. 24. So we've got an N in the middle, O around it. Doesn't matter where you put them, but as long as they're around it. Bond to each. That's 2, 4, 6 electrons. I've got 18 to go. The octet rule for the outer atoms, this oxygen needs 6 more. This oxygen needs 6 more. And then this oxygen needs 6 more. I've got none left, right? That's important. None left. But the central atom does not have an octet. So I need 2 more electrons somehow. I cannot just draw them in. I have none left. And so I'll have to share. So I will take a pair from one of the oxygens and move it between the nitrogen and oxygen as a double bond. Now, why did I take it from this oxygen? This coincidence. I could have taken it from this one, I could have taken it from this one. And this is the big clue that we have resonance structures. So these are the three different resonance structures we're going to create. So one of them is going to look like this, where I borrowed it from the bottom. The other one is going to be when I borrowed it from the top right. And then the last one's going to be where I borrow the electrons from the top left instead. So these are the three resonance structures. Okay. What I'm leaving off here is the brackets, square brackets with the minus sign on it, but that's okay. Next, how do I calculate the average bond order? So what I'm going to do is I'm going to take one structure, just one, and look at the bonds that are involved, which is just these three. And one of them is a single bond. The second one is a single bond. The third one is a double bond, bond order 2. And I've basically looked at 3 of those bonds, divided by 3. So 1 plus 1 plus 2 is 4. 4 thirds, which is 1 and a third. Or 1.3, whatever you want to say. Same thing. So there it is. The bond order of the nitrogen-oxygen bond in nitrate is 1.33, 1 and a third. So we got a little bit of, different answers here, but it's okay. This is a new idea. What's going on? There we go.
Just to be clear,
Yeah.
all of those resonance structures are equally as good.
Yeah, I didn't even, you're right. I didn't check it. But if I do formal charge calculations on these, just for fun, the nitrogen's always a +1. Right? And I can show you the calculation if you want. It's 5 valence electrons minus 0 lone pair electrons minus half 8. Because there's 8 bonding electrons. So the nitrogens are always +1. The double bonded oxygens are 0. And the single bonded oxygens are -1. And one of the rules of formal charges is that the formal charges have to add up to the overall charge. That's a way to check to make sure you did it right. Yeah, and there's an overall minus charge, so they should add up. Plus, minus, and minus give you minus. So they're all equivalent. There's no one that's better than the other. They all have a plus on the nitrogen and a couple negatives on the oxygen. I can't make this better by doing a second double bond because nitrogen cannot break the octet rule. Nitrogen's row 2, doesn't have d orbitals, so it has to be like this. Okay. So these are equivalent resonance structures. So what is the true picture of this thing? It's going to look, I mean, I can't draw 1 and a third bond exactly, but it's 1 and a little bit like this. That's the real picture of nitrate ion. And we can verify it. We can measure the bond length of any of the NO bonds, and they're all the same.
And those with dotted lines mean that it can be any of those double bonds?
Some fraction of a bond, yeah. The dotted line means really nothing. It just, so it's not a proper Lewis structure, let's put it that way. Yeah, so 1 and a third. Okay. What about formal charges on the hybrid structure? All right, so there's our hybrid structure. That's kind of what it really looks like. What would the formal charges be? Well, it's also an average, but we're going to do it a little bit differently. Look at the nitrogen. In every single one of these Lewis structures, these resonance structures, it's always +1. So the average formal charge for nitrogen is +1. That's not changing. But what about the average formal charge on, for instance, the bottom oxygen? On this one, it's 0. On this one, it's minus. On this one, it's minus. So if I average that out, 0 and a -1 and a -1, how many? There's 3 structures, so -2/3. So the formal charge on every single oxygen is not a -1 or a 0, it's -2/3. And
Sorry, is that the hybrid structure?
this one's the hybrid structure, yeah. The resonant hybrid, yeah. So why would this make sense? Why would this be useful? I mean, remember our guidelines for formal charges. We want small formal charges, that's better. And a -2/3 is not a full -1. It's a little bit less, it's a little bit more stable, I should say. That's a better way to put it. Alright, so resonant structures help stabilize atoms, or molecules, excuse me. Alright, they make more stronger bonds, they spread out the formal charges a little bit more, and that's why they exist. Or it's one of the reasons that they're useful. Okay. There it is. Okay. So how do we explain this with atomic orbital theory? So, meaning, you know, when I look at an atom that has s and p orbitals, and we've kind of talked about, in general, to form a covalent bond, these orbitals have to interact somehow. How do we explain all this bonding with those? So let's start from the basics. And so here we are, we've talked about atomic orbitals, we've talked about Lewis structures and the VSEPR model, which is the shape. Now we're going to get into valence bond theory. This is going to be basically how we describe bonding using the orbitals themselves. Okay? So we'll start from the most basic of basics, hydrogen molecule. So hydrogen molecule H2, each hydrogen has a 1s orbital, that's it. That's all there is at energy level 1. And the hydrogens come with 1 electron each. So there's a single electron in there, there's a single electron in there. And they want to share each other's electrons. They want to look like helium, the noble gas. They want to have 2 electrons, both of them. So they're going to share each other's electrons. The electrons are in the orbitals, so to share them, the orbitals have to overlap a little bit. And there it is. There's the overlap. And so now these 2 atoms can share their electrons. That's pretty much the basics on how bonds form between orbitals. It's pretty simple so far. What about more complicated things? So fluorine and hydrogen will make a bond. Why are we using the 2p of fluorine? Well, here's one reason why. Let's remember what the orbital diagram of fluorine looks like. So fluorine, if I have an energy diagram, it's got a 1s orbital, which has got 2 electrons in it. That's the first shell. And then the second shell, there's a 2s, and then there's a bunch of 2p's. And fluorine has 7 valence electrons. So 1, 2, 3, 4, 5, 6, 7. So fluorine would like to have an octet. It wants to fill up its final energy level. It needs 1 more electron to do it. It's going to share electrons with hydrogen to do it. And that electron that it needs to fill up that last p orbital. And that's what this p orbital is. This is a p orbital that has 1 electron only in it. It's going to overlap with the hydrogen. It's 1s orbital. You're going to share each other's electrons. So fluorine will fill up that 1 spot. Hydrogen will fill up its 1s spot, and that's it. 2 fluorines do the same thing. So how do you make F2, which is the natural form, the elemental form of fluorine? Well, it's that same p orbital, but now you get 2 of them, 2 sets of fluorines. They each want to fill up their last p orbital with electrons. And so they'll each have p orbitals pointing at each other. They'll overlap like that, and they'll share electrons. Okay. That's simple, though. That's only for molecules that are binary, like just 2 atoms. what about more complicated things? So how do we go from these s orbitals, which are spherical, and these p orbitals, which have these 90-degree angles, right? They're oriented in 90-degree orientations. How do we go from that to 109.5 for tetrahedral? How do we go to 120 degrees for trigonoplanar? So this is where it's a little bit complicated. We have this concept called hybrid atomic orbitals. Okay? And so remember what an orbital really is. An orbital is this region of space where we're likely to find an electron. Remember where we get this concept of orbitals from. We get them from solutions to the Schrodinger equation, which these are wave functions. They're just mathematical equations. And since they're mathematical equations, we can manipulate them. We can do some interesting stuff with them. If you're taking any linear algebra, that's pretty much what is happening here. We're going to combine multiple equations, multiple orbitals, and make new orbitals out of them. We're going to make these hybrid orbitals. So, the goal is to make new orbitals that are pointing in the correct orientations to make these angles that we've come to be familiar with. Tetrahedral bond angles, 109.5. How do you get the orbitals to point downwards like that at these angles? So, hybrid orbital theory. And this movie doesn't work, so I'm going to have to draw it on the board. But we're going to start with this concept of sp3. So, first let me focus you to the shape. All right? Anytime you have a tetrahedral electron geometry, your central atom, which makes that tetrahedral electron geometry shape, has to convert its orbitals into these new orbitals, these new hybrid orbitals, called sp3 hybrids. So, what is happening? So, for instance, if we talk about methane. Now, methane is like this, tetrahedral. That carbon has s and p orbitals. It's 2s and 2p orbitals. That's what it's using to do bonding with. But they're not s and p orbitals anymore. What is happening in order to make this shape is the s and the 3 p orbitals on the carbon are mixing together and turning into 4 new orbitals. So you put 4 orbitals in, you'll get 4 orbitals out. These new orbitals are called sp3s, sp3 hybrids. The label says what went into it. A single s and 3 p's combined into these new things. And I'm not going to show you the math because I can't, but the result is you get these orbitals that are pointing in the tetrahedral directions. So you get one goes up like this. You get one that goes in each of those 3 positions at the bottom of the tetrahedron there. So all together they look like this, and they have these bond angles that are perfect now for tetrahedral. 109.5. So that is tetrahedral. That is sp3 hybrid orbitals. So again, whenever you see tetrahedral electron geometry, think sp3 hybrids. sp3. So here is methane, and so now the hydrogen's 1s can overlap with the sp3 hybrid orbital now, and there's 4 of them. So here's an sp3 pointing at this hydrogen, this one's pointing at this hydrogen, and you're making that perfect tetrahedral shape there. So that's where these weird bond angles come from. The weird bond angles come from hybridizations of these orbitals. And again, I'm not going to show you how that works, it's math, but this is what happens. All right, now, what about other tetrahedral shapes? So ammonia and water are also tetrahedral electron geometry. Okay, ammonia's got 1, 2, 3, 4 groups of electrons. So does water. 1, 2, 3, 4 groups of electrons. The molecular geometries are not tetrahedral, but the electron geometries are. Well, these are also sp3s. So before I show you that, let me show you what happens to the let me show you what happens to the orbital diagram. So here's carbon, right? And I'm just going to do the valence orbitals. So carbon has the 2s and the 2p's. And the electrons are going to look like this. Carbon has 4 valence electrons. So this is carbon by itself, right? Carbon atom alone. Now, when it tries to make a bond with the hydrogens, it makes methane like this. These will hybridize. And when they hybridize, they make new orbitals. And the new orbitals are somewhere in between the energy. And they all are the same. And I'm going to label them sp3 orbitals now. They're sp3 hybrids. So these orbitals all mix together to create these new ones. And remember, there's still 4 valence electrons. But look what happens. Since these are degenerate, these are the same energy now. 1, 2, 3, 4. And you can see that I have a spot for each hydrogen to bond to share electrons with. So that's what happens with the orbitals. The orbitals, again, they mix together, create these new orbitals that have new shapes, and those are what bond with the hydrogen s orbitals. So now we get to ammonia and water. The same thing happens. We get sp3 hybridization because it's tetrahedral electron geometry. But it's a little different because ammonia has 5 valence electrons. So the 5th valence electron, notice, pairs up with that first one. And that's what the lone pair is. There's no need for bonding here because we already have a full orbital, and that's a lone pair. So there's spots for 3 other atoms to bond, and that's why ammonia is NH3, not NH4. Water is the same way. Oxygen has 6 valence electrons. So here's the original oxygen. It's 1, 2, 3, 4, 5, 6. After they hybridize, make these sp3 hybrid orbitals, you've still got 6. 1, 2, 3, 4, 5, 6. Hund's rule, 1 in each. First. And I have 2 lone pairs already. That's those. And I've only got spots for 2 atoms to bond. So this is kind of the how these bonds form with these orbitals, okay? We've kind of learned what they're going to do, but we needed a little bit more information on how they do it. So this is how they do it. Okay. It can get a lot more complicated than this, but it's not going to. Okay. So, what about other shapes? Okay, so tetrahedral, we have sp3. With trigonal planar, any trigonal planar shape, so BF3 and CH2O. CH2O is formaldehyde, which looks like this. So there's 1, 2, 3 groups of electrons around the carbon. That's trigonal planar. In your mind, you should be like, trigonal planar is sp2 hybridization. So what is sp2 hybridization? It's exactly what the label says. An s and 2 p orbitals mixed together. Just 2, not all 3. So the s and 2p, that's 3 atomic orbitals mixed together, and they will make 3 hybrid orbitals. And coincidentally, those 3 hybrid orbitals are oriented perfectly for trigonal planar, 120-degree bond angles. We're going to ignore the unused p orbital for a second, but there is an unused p orbital here. We didn't, like, there's 3 of them, right? We only mixed 2 of them in. So there's 1 that's not being used. We'll come back to that. So next shape, linear. So linear, like not 2 atoms, but 3, like carbon dioxide or something like that. With linear shapes, it's sp hybridization. sp meaning 1 s, the only s, and 1 p orbital only mixed together. And if you mix together 2 orbitals, you get 2 hybrid orbitals, and they coincidentally point opposite directions. One points that way, one other points the other way. Perfect for your central atom carbon and your oxygens on either side. Okay. sp3, it's 1s, 3 p's, that makes 4 sp3 hybrids. sp2, sp, and so forth. So this is a nice little summary of kind of what we've gone through so far. These are the 3 shapes. And of course there's the higher level shapes too. There's trigonal bipyramidal, there's octahedral. But we're not going to cover those in the final. So don't worry about them. You'll see them in the homework, but the trigonal bipyramidal and octahedral, the 5 and the 6
Oh, yeah.
position ones, yeah. So they have also special hybridizations. We'll mention them, but we won't cover them in the final. So let's focus now on this last part. So on sp2 with trigonal planar, we're mixing the s and 2 of the p orbitals. So there's 1 leftover p orbital we didn't touch. And with sp hybridization, there's actually 2 leftover p orbitals we didn't touch. There's nothing left for sp3. So what's happening with these leftover p orbitals? And that's actually pretty critical. So we're going to go to, I'm not going to move on. We're going to go to a molecule called ethylene. Technically it's called ethene, but it's ethylene commonly. C2H4. And the Lewis structure looks like this. So if I look at the shape around the carbon, each carbon, so for instance that carbon, 1, 2, 3 groups of electrons. That's trigonal planar. Planar, electron geometry. So if it's trigonal planar electron geometry, I know immediately the hybridization on that carbon is sp2. Okay? That's the same for this one. This carbon is exactly the same. Trigonal planar, sp2. Okay, so if I were to imagine, well, what are the orbitals doing? Like, what kind of overlaps are they doing? Well, this carbon has 3 sp2 hybrids, one pointing that way, one pointing that way, one pointing that way. They make the shape. So if I put a little carbon in the center, I'm just going to draw the main lobe that points that way. One pointing that way, one pointing that way. And then there's a carbon on this side, and that carbon has a lobe pointing that way, and then one goes that way, and then one goes that way. And then there's hydrogens over here. So actually, let me label those real quick. So these are all sp2 hybrid orbitals, all of these. And I don't even have all the arrows. I'll do the hydrogen. So the hydrogen's using 1s orbitals to overlap, right? So before we move on, I want to talk about the kind of overlap that occurs. And we haven't talked about it yet because it hasn't come up, but anytime you have this end-to-end overlap of orbitals, more specifically you can define it as an overlap of orbitals in only one spot at a time. This is called what is known as a sigma bond. So that's the Greek letter sigma. I write sigma S-I-G-M-A. So that's a sigma bond. All of these are sigma bonds. Every single overlap that you see here is a sigma bond. And it's not a coincidence. Sigma bonds happen wherever there are single bonds. Okay? And they're defined, again, sigma bonds are anytime you have this end-to-end overlap of orbitals. Another way to think of it is an overlap of orbitals in only one spot. So these two orbitals overlap in one spot only. But what we haven't talked about yet are the p orbitals. So despite the carbons having 3 sp2 hybrid orbitals, they also have, I'm using the color here, each have 1 leftover p orbital. that p orbital is actually pointing in and out of the board. So there's a, remember p orbitals look like this, kind of this dumbbell shape. So one of those lobes is pointing out of the board, the other lobe is kind of pointing into the board. Right? They're perpendicular to this blackboard thing. So if I rotate this sideways, I'm going to try to do my best to draw it with a little bit of perspective. If I rotate this sideways, I'm going to just draw the bond here like that. The hydrogens are kind of like that. So now I've turned that molecule sideways like that. And so the p orbitals are like that. And I wish I'd drawn them a little bit fatter, but notice what happens to the p orbitals. They are overlapping in two spots, above and below the bond axis. So the bond axis is here, and the p orbitals are overlapping in two spots here. This is what is known as a pi bond. And this is another type of bond that can occur, so pi bonding. So the p orbitals that are left alone or unused are equally important. And in this case, remember what the Lewis structure is. There is a double bond between the two carbons. So the first bond of that double bond is the sigma bond. The second part of that double bond is the pi bond. So there's a pair of electrons here, and there's a pair of electrons in these things too. And that's where the double bond comes from. So, I'm not going to try the next one, but so there's two kinds of bonds. There's the sigma bond and the pi bond. So remember that. Most of them are going to be sigma bonds. You're only going to see pi bonds when you have double or triple bonds. And even though it's not under our umbrella, we're not going to worry about it. You don't have to have just two p orbitals to make a pi bond. You can use d orbitals too. And there's more bonds than just these. But these are the common ones. So there's like a delta bond too. But don't worry about those. There's more than just this. Let's put it that way. So let's. Did they fix the clock? It is fixed, right?
Yes.
Okay, good. It wasn't fixed yesterday. All right. Let's take a quick break by doing these questions on page 263, 1 through 5. They're not difficult. They just kind of reframe your mind, make sure you're taking a break, understanding this, putting things in your own words so that they sink in better, and then we'll continue. to, no, we're not gonna cover anything more than that. So we're getting close to your question of is there a hole in the middle of the benzene?
Right.
So the pi bonding is starting to, will play a role in saying yes or no. We'll look into that.
Right.
You'll see a picture.
What's it asking for when it's asking for the shape of that?
This is just kind of in your own words so that you're straight in your head.
Just describing the overlap? The shape
Yeah.
of the overlap?
What's the characteristic shape? Yeah. Just like I said, this is just to kind of reframe it in your heads. You don't memorize definitions. You're just thinking it.
What's the electron density?
Electron density is kind of a description of where you're most likely to find electrons. So high electron density, you're have a good chance of finding them there.
So that overlap area is high electron density.
Generally, yeah,
Okay.
yeah. Yeah, p orbitals have characteristic 0 electron density right at the atom, and then pi bonds have 0 electron density along the axis, right? Yeah. Yeah, these ideas of looking at orbitals and where they are, it's a big deal for any other chemistry level class. So like organic is when you'll start thinking about bonding using p orbitals like this. Like it'll make sense. You'll be like, oh, that makes sense. So this is a good tool for your toolkit if you're gonna take more.
So for the characteristic shape,
Mhm.
the sigma bond would be parallel with the proline. Is that what you're trying to ask?
I mean, this is in your own words. There's no right or wrong. It's very subjective description. That's it.
For art class, so fun.
Huh?
Art class.
Yeah, it's what makes sense. It's a teaching technique. If you can put it in your own words what it looks like, it makes you remember it better. That's it.
Fair enough.
I have mixed feelings about some of these exercises. I understand where they're coming from, but sometimes they get a little bit patronizing. Sometimes. That coupled with the fact that some of these are oriented to high school.
Oh, yeah.
So they're a little bit, yeah, but it works, so.
This is like an AP chemistry class, right?
Yeah, oh definitely, not regular high school, yeah. Yeah, depending on which high school chemistry you got, you can almost skip out of some gen chem classes. I did. I went to Lincoln and I did the 2 years IB chemistry. And I still didn't get a good, I mean, I got a good score. I didn't get like a really good score on the IB exam. I think I got 5 out of 7, which is passing, a little bit better than normal passing, but it's not 6 or 7.
Well, I did IB physics really bad.
It was bad. My college, when I went to undergrad, still made me take a placement test. They were like, oh,
Yeah, fair enough.
yeah. And I was like, oh, no problem.
No problem.
Generally, it's the sigma bonds are high electron. I guess that's like because they have a overlap, or rather than just a five touching at the top. Or is that wrong?
Well, no. So they're saying with respect to the internuclear axis. So along where the internuclear axis is the space between the two atoms. So the pi bond says no electron density.
Oh, so they're showing that. Okay.
Yeah.
That makes sense.
Okay. Actually, let me get to this. Hold on a second.
Really didn't
I'm going to assume that everybody's okay with the first four. At least question 1, hydrogen S orbitals only. The rest of them S and P. You know, that's it. There's no d orbitals involved because none of those are from period 3 or anything lower in the periodic table. So 2 and 3 are very subjective. You'll have to, and 4, you'll have to describe what you think. The takeaway from 4 is that you see that this internuclear axis, the axis between the center of the atoms, for pi bonds, there's nothing there. Whereas for sigma bonds, there's plenty of electron density between the actual nuclei, directly between. Okay. And the last one, if a bond is a single bond, what type is it? Sigma. Yeah, so sigma is always the default first bond for these general structures that we're going to do. You only get the pi bond when you start doing the double bond, and then we'll see the triple bond too. Okay. So there we go. Sigma bond, pi bond.
For one.
Go back. Yep, right here. So these are all examples of sigma bonding, whether they're from regular orbitals or even hybrid orbitals, doesn't matter, as long as they overlap in one spot, and that overlap is along the internuclear axis right there. Here's better probably pictures than I drew, but we needed to do step by step because this is a little busy. Here's all the sigma bonds, or at least the sp2 hybrids for the 1 carbon, plus the p orbital. And then here's the 1s orbital on the hydrogen. So that's exactly what I drew. And then once you take away all the sigma bonding stuff and just leave behind the p orbitals, you can see that the p orbitals do this side-to-side overlap. Every artist will do it slightly differently. I mean, I drew mine where they were that close together. They just kind of fudged it. So it really doesn't, you depending on what picture you'll see, it looks a little bit different. But again, the p orbitals are oriented where they can be side to side like that. Here's another view of the same thing. And so here, instead of using these very stylized orbitals like this, I think this is a slightly better kind of representation of what the p orbital shapes look like after they overlap. They kind of just make this big smear like that. So that's kind of a better picture of what it looks like. But again, it's a different version of the same thing. So yeah, the 2p orbitals. So there you go. These yellow things are the hybrid sp2 orbitals. And there's 3 of them on each one. And the blue thing sticking out is the leftover p orbital. So these are like actual size orbitals kind of thing. And they do that, and so forth. And here's another way to look at it. Same orbitals, just kind of different artistic rendering of it. I think what we're doing is just pulling out pictures from different books and just showing it. It's all slightly different, but it's the same thing. Okay. There we go. All right, now, here's a new one. This one's really busy looking. So what we're looking at is ethine. That's the formal name. The common name is acetylene. So this is acetylene gas. If you do welding, gas welding, use acetylene and oxygen. And it's there, but I'm going to draw it on the board again. That's the Lewis structure. And if you look at what is the shape around this carbon, 1 group, 2 groups of electrons, linear. 2 groups is linear. Linear electron geometry. So in your head, you should be like, oh, linear sp hybridization. sp. So that's exactly what happens. Each carbon does sp hybridization. You get 2 sp hybrids. One going that way, one going that way. These are 2 different orbitals. And then there's 2 leftover p orbitals. So again, p orbitals have 2 loads like that. Here's one sticking up and down. The other one is going in and out of the board. And same thing with this carbon. So you get the sp, they get the sigma bonding. There's the sigma bonding with the sp and the hydrogen on the other carbon, and then the sigma bonding between the two carbons. And then we have two sets of pi bonds. We've got the pi bonds from the vertical p orbitals that do side-to-side overlap like this, like these two things right here. And then you've got the p orbitals that are going in and out of the board like that, and do side-to-side overlap. So there's this thing, and then there's a blob behind it that you can't see. So there's two pi bonds in this one. So between these two carbons, there's a sigma bond and two pi bonds, and that's where the triple bond comes from. So it's pretty difficult to see it sometimes, but what you see down here is kind of a description of the bonding. So between the two carbons, there is a sigma bond between a sp on one carbon and an sp on the other carbon. There's a pi bond between a 2p and a 2p on each carbon, and a second pi bond between a 2p and a 2p. And in addition to that, there's a sigma bond between sp on a carbon and a 1s orbital on the hydrogen. Yeah?
So, in that first picture on the left, top left, it's
Uh-huh.
got the sp is only one p orbital, but the other two in each of them are just p orbitals. So why does that happen?
So I think probably the sp hybridization is probably the easiest to visualize. So what you're doing is you're mixing the 2s orbital, and one of the two p orbitals, the one that's in this direction.
Oh.
And when you mix these two together, you get an sp hybrid that looks like that, and an sp hybrid that looks like that. So what we're not showing is the second part of the lobe. It's much, much smaller. We kind of just ignore it a lot of the time.
But so why do you get two lobes like that? I mean, it doesn't look much different from a 2p orbital anyways.
So, okay, this is linear combinations. So what is happening, we haven't talked about phases of orbitals or anything like that, but orbitals have phases, just like waves have phases, right? They can go up and down or down and up. P orbitals have a plus and minus phase, and then s orbitals are either plus or minus. So what's happening is when I mix these two together, what happens when they're in phase? They add, and when they're out of phase, they subtract. So when I put these two together, I get this one. And when I subtract one from the other, or imagine the opposite phase, I get this one. That's the linear combination. That's the algebra that we're talking about. So these are the two sp hybrids that you get.
And since there's only one s orbital, that only consumes one p orbital to do that, and then there's just two leftover p orbitals.
Well, I think you're kind of, the way you said it, you're saying that there's like some cause and effect there, but to get the linear shape, it's just one p and one s mixing together. That's it. If it needed to do the trigonal planar shape, it would be an s and two of the p's mixed together. And if they needed to do the tetrahedral shape, it would be all of the p's and one of the s and the s's mixing together. So the number of orbitals you mix together tells you how many hybrid orbitals you get out. So I mix two orbitals together, I get two hybrids out.
Alright.
It's the best I can tell you at this point.
Yeah.
Okay.
I'll keep going.
Yeah, and you know, so this is one, that's the other. Like these little tiny lobes that are left over, we ignore those. They're just small. They don't do anything. Not at this level, they don't do anything. So coming back to benzene and this idea of delocalization and how these electrons can move around. So let's kind of look at what's happening with benzene. So benzene is sp2 hybridization. All right, sp2 around every carbon. It's trigonal planar. I can go back to the picture, but it's trigonal planar. So sp2, 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 and that's the framework that connects all the atoms together. And every carbon has one leftover p orbital that is pointing in and out of the board. So this picture here is you take this and you rotate it a little bit, and there they are, perspective-like, and they're all parallel to each other. And you know, if you're thinking a little naively, you might think, oh well, two p orbitals will mix together and make a pi bond and a pi bond and a pi bond. But why limit it to just two? They're all side by side. You can make one giant connection like this. And that's the picture of how these electrons are mobile. The electrons in the double bonds, the three double bonds that we normally draw, are actually not in those double bonds. They're allowed to go anywhere in the ring because they can move around all of those pi bonds there. So there it is. That's kind of the picture. This is why we treat benzene, that's why we draw benzene with a circle in it. Because that is really how it behaves. Those electrons are pretty much mobile in that ring. All right, not the single bonds, right? These electrons are stuck. They're between the atoms and that's it. Those are the sigma bond electrons. I'm talking about the pi bond electrons. Those can move around. Okay. There's another picture of benzene. So there is a hole in the middle. It depends on kind of how you kind of interpret if there's room kind of thing. So here there's clearly a hole, but here when you look at the electrostatic potential, there's a very strongly negative charge in the middle there. So it's complicated. Just in case, here's a little bit more advanced topic. And this is not an exam. I can't draw it exactly because it's very difficult, but graphite, or graphene that we were talking about, is a bunch of 6 carbon rings stuck together. I mean, not to infinity, but close, like this, and it just keeps going. But all of the p orbitals are all parallel. And then there's a layer, another layer on top, and another layer on top, and the p orbital lobes will interact with the p orbital lobes from the bottom layer. That's what makes graphite conductive. It's really weird how that works. Carbon is a non-metal. Non-metals are never conductive normally. But in this case, the way it's oriented, the way it's all constructed, you get kind of conductivity. So things conduct along that like high stack. It's weird. DNA works similarly. DNA is conductive along the stack of nucleotides through the same method. Anyway, there's a lot of interesting things going on. So there we go. Nitrate. We looked at nitrate briefly. Same idea. Same exact idea. So each nitrogen, this nitrogen is sp2, hybridized. There's a single p orbital on that nitrogen sticking up and down, which will interact with the p orbitals on the oxygens. And you get this nice delocalized pi bonding electrons again. Nicely stable that way. Okay. So, like I said, I was going to mention it. You don't have to be quizzed on it. But if you want to make any of the other shapes, how do you make trigonal bipyramidal? Well, we're going to add an extra orbital. And the next orbital we could add is a d orbital. Right? No more after the p's. They're all used up. And if you want to make octahedral, you add a second d orbital. Yeah?
So on the mastering chemistry in here, the tetrahedral bond angle is 109.5.
Mhm.
On the chem activity lab,
Uh-huh.
it's 109. Does it matter? Or-
They're just shortening it a little bit.
Okay.
I'll accept the 109. It's fine. Yeah. But again, we're not going to test you on the D stuff. So just in case you weren't curious, that's how we do it. Oh yeah. So we've got some weird hybrid orbitals when we get to octahedral and trigonal bipyramidal.
Okay.
Yep. So let's do a couple here.
Are these from our homework?
Was that?
Are these from our homework?
Oh, I guess they are, aren't they? Yeah, they are. So if we now look at hybridization on these things, for instance, ClO3. If you did ClO3 minus, this is chlorate. The Lewis structure, there's a couple different ways you could have done it. If you did it like this, that's fine. This is not the best structure according to formal charges, though. With formal charges, a better structure would be like that. But either way is fine. It doesn't matter because 1, 2, 3, 4 groups of electrons, sp3 hybridization. So that's it. All you have to do to know what the hybridization is to know what the electron geometry is. sp3 hybridization. CCl2O looks like this. Right there, trigonal planar. 1, 2, 3 groups. So sp2 hybridization along that carbon atom. And we only talk about hybridization on the central atom. If it's a terminal atom, there's no hybridization, just regular orbitals. So I think, we did a long, complicated discussion of this, but ultimately some of these questions are pretty easy to do. As long as you know the shape, you can find the hybridization. They do get a little more complicated, but there we go. So here's an example. This is glycine and amino acid. The amine part and the acid part, that's why it's called an amino acid. Hybridization around this thing is sp3, because there's 1, 2, 3, 4 groups, tetrahedral. That's sp3 as well, 1, 2, 3, 4 groups. That's sp2, because it's trigonal planar, and that's sp3, 1, 2, 3, 4 groups, tetrahedral. Easy to do. Once you're familiar with the shapes, that takes time. All right, here's where it gets tricky. Why don't you guys answer this? How many total sigma bonds and pi bonds are there in this thing? Sigma and pi, not single and double. There's a distinction. This is a good test question, too.
So not to give away the answer, but is the double bond does it necessitate a pi bond?
Say it again, sorry?
Is the double bond, does it necessitate a pi bond?
Yes. All right, we've got some good guesses in. Let's see, everybody's voting. Mostly people are voting D, but we've got other answers. So the answer is D. You have to count 1, 2, 3, 4, 5, 6 single bonds. That means at least 6 sigma bonds. But remember, this double bond actually has a sigma bond in it too. So every bond starts with a sigma bond. So there's 1, 2, 3, 4, 5, 6, 7 sigma bonds. And the second part of this double bond is the pi bond. So there's 7 sigma, 1 pi. All right, so tricky until you get used to it. So 6 starting plus an extra 1 on the pi, on the double bond, and then a pi bond from the double bond as well. Here's another good test question. What 2 orbitals are overlapping to make the sigma bond pointed to by that arrow? It's a little bit of a brain teaser here.
Great question.
So there's an orbital coming from the left side carbon and there's an orbital coming from the right side carbon, what two orbitals are they that make that sigma bond? Alright, you got 5 votes in. Just a little bit of time, if that's okay.
Just to be clear, the idea of hybridization, what does that actually affect in terms of your understanding of what's happening in a chemical process? It's just like you think about it, right?
A little bit.
Or does it help explain?
I think I talked to you about the LUMO and the HOMO thing, the lowest unoccupied molecular
yeah.
orbital. A little bit of that. So, knowing what the energies of the hybrid orbitals are helps us understand a little bit better about what the energies of, like, we're going to get to molecular orbitals next, but yeah, to understand that better. Yeah, but more hybrid orbitals is an explanation for why we get these shapes when the orbitals themselves have these strict shapes that don't conform to the geometric shapes we've been seeing.
Oh, okay.
That's it.
Yeah, cool.
Okay, so all over the place. So the answer is E. Majority rules in this case. Look at the shapes. So around the central carbon, 1, 2 groups of electrons. That's linear. Linear is sp hybridization. Around this carbon, 1, 2, 3 groups. 3 groups is trigonal planar. Trigonal planar is sp2. So sp from this carbon, sp2 from this carbon will make the sigma bond. Now, if the same question was what makes the pi bond, you would say a p orbital and a p orbital. That's it. Or 2p and 2p's, technically. Okay. All right. Next. Oh, yeah. Total number of sigma and pi. Alright, we'll stop there. And, yeah, everybody got it. Good. Alright, we're better. We're used to it now. So that's, we're so early, my god. Alright, that's it for today. I don't really want to do more, unless you guys want me to start the next set of slides, the molecular orbital theory now. It gives us more time to do review. Yeah, question?
So what exactly is going to be on the Thursday quiz?
Oh, good question. Thank you. So Thursday quiz, I'm just going to ask you about drawing Lewis structures and naming shapes. So I'm not going to do the dipole moment thing yet, or not yet. I'll save that for the final. But for the quiz, we'll just do Lewis structure like kind of with the homework quiz. Well, actually not with the homework because that's dipole moments too. We're just going to do Lewis structures and shapes. So tetrahedral electron geometry, trigonal pyramidal, molecular geometry, being able to write that, all that stuff. And I will stick with the basic ones, so like none of the octahedral or trigonal bipyramidal stuff, just the basic ones that you'll have in the final as well. Okay? In fact, while we're talking about future stuff, let's look at the practice stuff and the guidelines that should be available. Let me make sure that they can see them. Make sure you guys have access to them before we go. Alright, so exam review. Oh. Now you do. So I've got a sampler. I'm going to look to see if I have more than that, but there's a small sample of problems. I think, oh, is it working? Come on, slow. Try it again. There it goes. Yeah, it's not, oh, that's just pretty big. 14 pages, okay. So it's bigger than I thought. Yeah, so you can see we've got basics of basics, all the SIG-FIG stuff. And then it goes all the way up to quantum mechanics and stuff that we covered. And then here we get bond length. This is the new stuff. We got Lewis structures, shapes, all this stuff. So, you know, it's a sampling of everything. I would definitely look over the old practice exams, make sure that they make sense to you. Your old exams also. And yeah, there's plenty here.
Is the final gonna be the same length?
Yeah. Yeah, I'm not going to make it super long. I mean, it's 2 hours. That's usually, if you're fine, you'll do it in less than an hour or just under. So it should be okay.
Is this the same weight?
Sorry?
Same weight as your midterms?
Yes, it is. Yeah. It's 20% of your grade. Each midterm is 20% as well. So yeah. All right. So let's just end early today. Is that okay? If you want to stick around and